How do we make semiconductors conductive? As discussed so far this week, we need to excite electrons from the valence band to the conduction band to make semiconductors conductive. This can be achieved by several different routes. First, we can excite charge carriers using thermal energy. Secondly, we can use impurities in the semiconductor material. This is what we call doping. The third option, which is very important to solar cells, is to use the energy in light to excite electrons from the valence band to the conduction band. Before I will discuss these various routes to excite charge carriers, I will first discuss the important concept of the Fermi level. Let's consider a metal. Electrons are filling the electronic band of a metal. The electronic band is a band of continuous energy levels. This band is not fully filled by electrons. The probability to find an electron is not the same at all energy levels. At low energy levels, you will have a probability of 100% that electrons fill this level, while at high levels, this probability is close to zero. The probability to find an electron can be expressed by the Fermi-Dirac distribution function. This function reflects the probability that an electron will occupy a state at an energy E. Low in the valence band, this function is equal to 1, whereas high in the conduction band, this function is equal to 0. Note that this equation is only valid for a material that is at thermal equilibrium, which means that no additional energy is coupled into the system by electrical biasing, light absorption or heat conductivity. The Fermi level represents the energy level at which the electrons have a 50% chance to occupy the energy level at any given time. For a metal, it's easy to see where the Fermi level is positioned. Physicists use in general the term Fermi level. Chemists might use a different term. They might call this level the total chemical potential of an electron. The shape of the Fermi-Dirac distribution does change with temperature. At absolute zero, which means a temperature of 0 Kelvin or minus 270 degrees Celsius, the function looks like a step function. The probability to occupy a state below the Fermi level is 100%, whereas the probability above the Fermi level is 0%. For higher temperatures, this distribution starts to broaden around the Fermi level. Around the Fermi level, the energy is distributed over values between 0 and 1. The higher the temperature, the broader the distribution around the Fermi level will be. As you can see, a metal has only one electronic band. However, for semiconductors, this situation is different. The valence band is almost fully filled with electrons, whereas the conduction band only has a very few electrons. The Fermi level is positioned in the forbidden band gap between the valence and conduction band. According to the Fermi-Dirac function, electrons have a 50% probability to occupy the electronic states at the Fermi level. Since no electronic band exists at this level, in the forbidden band gap, no electrons can occupy this level. So the real distribution of electrons over the two electronic bands become more complicated. In general, the Fermi-Dirac function shows that the energy levels in the conduction band have a low probability to be occupied, while the energy levels in the valence band have a high probability to be occupied. At absolute zero, a temperature of 0 Kelvin or minus 270 degrees Celsius, all electrons fully occupy the valence band. The semiconductor material is not conductive. If we increase the temperature, the shape of the Fermi-Dirac function broadens around the Fermi level and some electrons have the chance to occupy the conduction band as well. The higher the temperature, the more electrons can occupy the conduction band. This demonstrates the physical principle that if you heat up a semiconductor material, it becomes more conductive. Using the Fermi-Dirac function, you can tell something about the distribution of holes in the conduction band as well. The positions in the valence band at which the electrons are missing are the locations at which the holes are present, indicated by the blue dots again. So if we remove the fixed electrons in the valence band, we are left with only the mobile charge carriers, the free electrons and the free holes. 1 minus the Fermi-Dirac function shows for a semiconductor the probability that you will find a hole at a certain energy level. This week, we will focus on the behavior of the charge carriers, electrons and holes in a semiconductor. We will use the semiconductor material silicon again as an example. And again, I will make a drastic simplification. The silicon network is a three-dimensional network, as you can see in this animation. The blue spheres represent the silicon atoms and the red dots represent the valence electrons in the molecular orbitals which are forming the bonds with the neighboring atoms. To illustrate the behavior of charge carriers in the silicon lattice, I will flatten the material and consider the silicon lattice to be a two-dimensional squared lattice. In this two-dimensional network, every silicon atom has 4 bonds with its neighboring silicon atom, like it has in a three-dimensional network. In this schematic silicon network, we put some charge carriers. The animation shows the mobile electrons, which again are indicated with the red dots. Secondly, we show the holes, which are in this illustration indicated by the black dots. They are part of a molecular bond in which one of the 2 valence electrons is missing. Both electrons and holes can move freely around. So far, we have discussed that we can manipulate the density of the free charge carriers using temperature. The higher the temperature, the more free electrons and free holes can be excited. Another approach to increase the density of the charge carriers is using doping. Up to now, we have considered pure semiconductor materials without any impurities. These semiconductor materials are called intrinsic. It means that the density of the mobile electrons and holes are the same in the material. We can intentionally incorporate impurities in the material. This is called doping. Doping can have a significant effect on the charge carrier density, which I will explain now. As an example, we take again silicon. Silicon is a material which has 4 valence electrons. In the periodic system, silicon is part of the column with atoms having only 4 valence electrons. At the left side of the column with 4 valence elements, we see that we have materials with only 3 valence electrons, like boron, aluminum and gallium. On the right side of the silicon in the periodic table, we have atoms which have 5 valence electrons, like nitrogen and phosphorus. First, we are going to intentionally put phosphorus impurities in the silicon network. Phosphorus has 5 valence electrons. The phosphorus atoms will make molecular bonds with its 4 neighboring silicon atoms. Since the phosphorus atom has 5 valence electrons, it has 1 electron left. This extra electron is easily excited to a free mobile state. The phosphorus atom left behind is not neutral anymore and becomes a positively charged entity. This positive charge is fixed to the position where the phosphorus atom is residing in the lattice. The result is that by adding an impurity, we have 1 extra free mobile electron and a fixed positive charge in the background. This is called n-doping. For n-doped semiconductors, the electrons are called the majority charge carriers, as the density of the electrons is much higher than that of the holes. The holes are called the minority charge carriers in an n-doped semiconductor. N-doping of silicon can also be illustrated by an electronic band diagram. The phosphorus atoms are represented as donor states. These donor states have an energy level within the forbidden band gap of the silicon matrix, which can be occupied by electrons. The energy level of the donor states is closer to the conduction band than to the valence band. This means it requires much less energy for an electron to jump from the donor state to the conduction band than for an electron from the valence band to the conduction band. At typical room temperatures, many to all of the electrons in the donor states can be excited to the conduction band. As a result, we have more free mobile electrons than mobile holes in an N-type semiconductor. We call the states donor states because they donate an electron to the conduction band. The electrons are the majority charge carriers. The holes are the minority charge carriers. As the electrons are the majority charge carrier, the Fermi level will be closer to the conduction band than to the valence band.